Tonight's speaker has over 16 years in medical informatics at Columbia University, is a senior solutions architect at Basho. Please welcome Alexander Sicular, who goes by Sasha.
Before I get started, I think the cool thing for me to do would be to take a picture of this audience, because nobody ever likes to hear me speak, but thank you for coming. I'm actually taking a selfie. This is true. Again, thank you guys for coming. Really appreciate it. You know, we got a lot of stuff to go over today. Please feel free to ask some questions. And I understand it's a little bit awkward with this kind of setup, but I'm going to make it work. So who's used Riak? Hands. Okay, thank you. Thank you for that. Appreciate it. What is Riak? We're going to talk a little bit about Riak itself, the KV architecture, key value, how it's architected, and then we'll continue the conversation with some of the new features and capabilities that we recently released when GA, maybe a week or two ago, had been announced over the summer. So I'm Alexander Sicular, I call me Sasha. I've been at Columbia University for many years, writing applications in the healthcare environment, obviously. Lots of relational expertise, like I'm sure a lot of the people in this room have. And around 2009, I started getting into non-relational systems. I was actually at the first public announcement of Riak at the New York City NoSQL meetup in 2009, fall 2009 here in Manhattan. And one of the original engineers came up and gave a little lightning talk about Riak, and I immediately recognized it as direct lineage from the Dynamo paper, which I already read in 2007. So at Basho, basically, I run around as a solutions architect, and I speak to folks about how you could implement Riak in your environments. And I noticed a lot of faces here. I'm from New York originally. I've gone to many of these meetups and seen a lot of you. Thanks for coming. So I'll kind of, fantastic. So I'll kind of thread the conversation through what might seem like a contrived example, but in reality, I come across a lot in my conversations with customers. Run an example through Riak KV, layering on search capabilities, layering on caching capabilities, then layering on analytics capabilities. You guys might recognize these folks. They have a website and mobile application, and they need to present that information to their customers, lots and lots of customers. And originally, you might have a product catalog. And this might be an architecture and what that might look like in its initial implementation's early state. You got your database, web is coming in and out of the database, the product catalog is feeding the database. But people have problems with that architecture, which is why we're all here talking about NoSQL in general. How do we make this work better? Eventually, you start looking at caching technologies put in front of your database. And so your architecture becomes a little bit more complicated. Check the cache, not in the cache, check the database, fill the cache. Very common design pattern. Well, let's talk about the realities of today and a company that you all probably know, and the things that they're trying to do. Internet of Things, collecting lots and lots of data from lots and lots of places, and then computing that data and presenting it to folks for ingest. More complicated, more caches. Mobile clients, mobile came along, everything became slow because you have to keep up with millions of folks. It turns out that we're all sitting up late at night playing with our iPhones and checking the Weather Channel. Now, how do we search this stuff? Separate searching out of the technology stack, putting in a separate search implementation like Solr or Elasticsearch. More complication in your architecture. This just continues to happen, and we've all been around this wheel a lot lately. And so what I want to kind of talk about today is how Basho is positioning themselves as a distributed computing company, where we have Riak KV as our persistent data store. The technology that really works behind that is distributed computing. And what we'll talk about here is how we're extending that technology to include other best-of-breed systems and applications to provide more functionality and capabilities inside of the environment. Riak itself is masterless. Those folks in the audience who try to or have successfully sharded relational systems like MySQL and Postgres, you usually shard on some dimension, time, for example. Inevitably, what happens is your data access patterns will disproportionately access one or more shards related to the rest. And in order to accommodate that, you're going to have to offset those shards with more hardware. Again, operational complexity. Riak, on the other hand, is masterless in its architecture, and all the nodes in the cluster are the same. They're all homogeneous. Every node in the cluster can execute every operation by design. The way that it does it is like so. This is the canonical image that you'll see whenever reading about Riak. Also very familiar to those who've read the Dynamo paper. Riak is able to do this by taking advantage of a unique property in the SHA-1 consistent hashing algorithm. The way you access data, again, in Riak is via key value. The key is some combination of a bucket and a key ID. For example, users/username, session/session ID, etc. That combination, in this case, artist REM, is hashed via the SHA-1 hash, whose output is some number in the 2 to the 160 space. So imagine a number line, 0 to 2 to the 160, turn it into a ring, and then segment that ring into equal partitions. We call those partitions virtual nodes, and the virtual node is the main layer of abstraction in Riak. It's basically where all the operations are happening, the data files on disk, etc. By default, the number of partitions or virtual nodes in Riak is 64, and it's a power of 2 because of power of 2 math divisibility into 2 to the 160. And that leaves you with equally sized partitions inside of the ring. In turn, those partitions in the ring, those 64 partitions in this case, default case, are equally allocated to the physical machines in the cluster. So for example, if you did have a ring of 100 virtual nodes, and you had 10 physical machines in your cluster, each physical machine would be responsible for 10 virtual nodes, 10 times 10 being 100. What that leads to is a unique property of Riak. Every machine in the cluster is responsible for one end data and one end performance. So again, thinking about this hypothetical 10-node cluster, each of the nodes in the cluster are responsible for 10% of the data and 10% of the performance. That's a unique property to consider as an architect or a designer or a developer or an operations implementer when scoping out the size of your cluster. How big do I need to do now? How big do I need to get in 12 months from now? What's my growth rate? Of course, all of this, a lot of what we'll talk about here today is directly derived from the Dynamo paper. Dynamo-based systems favor availability over consistency. So if you're familiar, for example, with the CAP theorem kind of governs properties of all persistent database systems. C is consistency, A is availability, P is partition tolerance. Generally, relational database systems are heavy emphasis C systems. They're consistent systems. Riak, on the other hand, is an AP system. The theorem basically states that you can only have two of the three, C or A or P, at the same time. Riak favors availability and partition tolerance over consistency in the general case. How does it do that? The system itself is continuously gossiping as to the state of all the machines in the system at any given time. Riak itself is written in Erlang, and Erlang is renowned for its distribution capabilities, its parallelism and concurrency, and network-based operations. You can run an Erlang virtual machine on one machine, an Erlang virtual machine on another machine, and simply say, send this function to this address in that virtual machine on that other physical machine. And that's more or less how Riak is working internally. When you create a Riak cluster, what you're really creating is a fully meshed network of Erlang virtual machines. Layered on top of that, and leveraging those language capabilities, Riak implements gossip. So each node in the cluster is continuously looking at the state of the cluster. In other words, which of the other machines can I see right now? And this is continuously happening. When a node fails, for example, the sibling nodes or the surviving nodes will recognize that failure and raise their hand and say, okay, I will now be the home or the secondary location for the virtual nodes that have primarily been living on the machine that failed. Internally, there's a Paxos algorithm running on different sets of machines inside the cluster. What's really interesting from an operational perspective when you look at building these systems, and the kind of question you need to ask yourself as an architect looking at these systems is not how the system operates in the general case when everything is good, but how do the systems operate in the degraded case while you're actively experiencing a failure. And the flip side of that coin, often left unanswered, is after you've recovered from a failure, how does your cluster rebalance itself? What happens? And those two questions play very prominently in decisions about distributed computing design. Riak, through hinted handoff, has a very good story about high availability. When the machine fails, surviving machines basically say, hey, I'm still here, and I will accommodate those write requests and those read requests for that segment of data. On the read side, on the recovery side, there are two capabilities here that are really at play. First is read repair, which basically is exactly how it sounds. As you read your data, you repair your data. So recall, might not have mentioned this, but Riak maintains high availability through replication. So when you write a piece of data into the system, it's replicated n times. And by default, n is 3, also configurable, globally and on a per bucket basis. So in order to write or read data, a coordinating node, because all the nodes are the same, so all nodes can receive, read, and write traffic transactions. And a coordinating node will then, on a write path, for example, issue a write request to the 3 machines it believes to be the owners for this piece of data, due to the SHA-1 hash and the virtual node allocation that we already discussed. So, by default, the first 2 of the 3 machines, or a quorum, to reply to the coordinator will instruct the coordinator that the request either failed or succeeded. So as long as 2 of the 3 machines are okay in a quorum scenario, then your transaction will succeed. And this is what we call tunable consistency. By default, the value is a quorum, or 2 out of 3, but you can tune that either all the way down to 1 for from maximum availability, or all the way up to N, where N is the number of replicas for maximum consistency. And you're in control of that. And you can set that at a global level, at a bucket level, or override it on a transaction by transaction level. And just to put a pin in that for a second, when I'm around and I speak to customers, the key concept to consider for those who have relational database experience is not that Riak is non-relational, in other words, unstructured. Rather, Riak is distributed, and relational databases are not distributed. That's the key consideration, and that's where you have to think about the access patterns as to accessing your data, looking for quorums, looking for one copy, looking for all 3 copies, et cetera, and how that affects your particular application. What's interesting about Riak is you can have different applications with different profiles, some of them tending towards availability, some of them tending towards consistency, all operating in the same cluster at the same time. The key advantage of Riak versus a lot of our competitors is multi-data center replication. So the way that Riak manages failures and outages internally within one cluster is the same kind of mechanic that it uses externally amongst multiple clusters. And our approach, Basho's approach to multi-data center replication is a cluster of clusters approach. So you have one cluster on the East Coast, one cluster on the West Coast, connect them together either unidirectionally, east to west, or bidirectionally, east to west and west to east. And depending on how you then distribute your clients, you can have an active, fully replicated in both locations or N locations topology. What's really interesting here is the hyper-flexible topology that you can create for your particular needs. And we have a number of customers doing a number of very interesting things here, and nobody's the same. Nobody has the same kind of needs. You can have, Tokyo feeding San Francisco, feeding New York, feeding London, and then all the way around. Or you can be in a system where you're building an application that you're delivering it to your clients, and your application is existing on premises, and they might have a central location and satellite locations, so you can manage a hub and spoke kind of model. And it's very, very flexible. There's a lot of configuration options there, et cetera. Yes, sir?
How does it scale with the Hyper-V replication?
Hyper-V replication? I'm not familiar with this.
That's a Microsoft virtualization.
Well, okay. Yeah, I'm not particularly sure on those details, but just for background purposes, Riak is a Linux installation, or Solaris, or SmartOS. As long as you can install in that environment, you can either install in native physical hardware or in a virtual machine environment or in Docker, for example. We have a lot of interest in people containerizing Riak. It's not fully supported yet, but we're moving in that direction, which is simply because of the interest. We do have Riak running on Azure, for example. Yeah. So we support it. We have customers who use it. As long as the Linux environment can exist somewhere, knock yourself out.
One question on the application. You mentioned about bidirectional application. Does it also have functionality such as peer-to-peer application can be set on such as virtual?
So the question is about a little bit more on replication, multi-data center replication, peer-to-peer potentially, and possibly moving from a binary system to ternary or in. Is that correct? Yeah, so this has to do with like the extreme flexibility or the hyper-flexibility of the topologies that you can create. So in fact, one of a very large customer of ours has 3 100-node clusters all connected in an active replication. And the 100-node clusters is not because they're necessarily working over a petabyte of data, but it's because their application has very tight SLAs as to how quickly they need to present data to downstream customers. So considering the 1/nth rule that I talked about earlier, with a 100-node cluster, you basically created, in aggregate, a very large pool, compute pool that can provide many hundreds of thousands of operations a second. But what's even more interesting than that is when you're actually developing these systems, I mentioned this earlier, you're not developing for the optimal case, you're developing for the failure case. So they're able to meet their minimum SLAs in the face of two-machine failure. So any two machines can fail, and your data, because it's replicated 3 times, is accessible on that third machine. And what's further interesting is, let's say you had a third machine failure. Only the segment, the fraction of data whose 3 copies were on those 3 machines would not be accessible. All the other data in your corpus would be accessible either with all 3 copies, 2 copies, or 1 copy. And that's how you can think about having various degrees of unavailability. So it's not a binary consideration. It's a little bit more creative than that.
That actually we highlight. The reason I was asking this question is, for example, if you have a global application, as opposed to having the network, latency or delay because of this network layer, the application point to run the server because of a time frame, might not have it.
Right, so if you have, so one thing is the question was around, well, application availability in the multi-data center scenario. So if you have your customer-facing applications that are co-located with each of these data centers, then they will continue to operate even in the face of a network partition. So the network partition is the P, the CAP theorem. And the P either works, that partition tolerance is either working against you it's continuously working against you at any time. When you start working with distributed systems, the network becomes a larger consideration in your calculations. And the larger your cluster becomes, the larger a possibility or percentage chance that you will suffer network partition scenarios, either within a cluster or over a LAN, where you have even a higher reliability on that network, or amongst multiple data centers connected over a WAN, where it's a less reliable link. Prone to congestion, for example. And so Riak has mechanisms for dealing with this sort of thing. Ultimately, in order to maintain full real-time replication between any 2 clusters, or any n clusters, your network bandwidth must meet or exceed your write throughput. So if you're writing 1 megabyte a second into the cluster, then in order to maintain real-time replication, your network must maintain. There's no magic there. There's no magic. We can't get over the laws of physics or the laws of Cisco. And that's just how it is. But something that's a new thing that's come up in the last few years in regards to multi-data center replication is geographical locality. It's usually been geographical locality for performance reasons. I have a lot of users on the East Coast, I need a data center on the East Coast. I got a lot of users on the West Coast, I need a data center on the West Coast. But now, since our friend Snowden and the NSA, et cetera, Europe is like, no. Data stays in Europe. So geographical isolation from a jurisdictional perspective is becoming more of a consideration for a number of our customers, specifically in highly regulated environments like finance and healthcare and government, for example. Some really interesting, so multi-data center replication is something that's very interesting, and the way that we approach that, in my opinion, is pretty novel. Something else that's interesting is that in the academia, there's a concept or an umbrella or school of work that's being addressed towards CRDTs. And CRDTs are convergent replicated data types or conflict-free replicated data types. And they're data types that are specifically designed to operate in a distributed environment. A lot of the research scientists who are at the vanguard of this field, a number of them actually work for Riak and work for Basho, and work to implement that academia in the product. Consequently, we have a number of different CRDTs available for people to take advantage of. Here they are, 5. The interesting ones, in my opinion, are counters and sets, for example. The opportunity to do distributed counting. So oftentimes you'll have an auto increment field in a relational database. The problem with relational databases, two main problems with relational databases. The first problem is the lock. The lock is what allows you to do the automatic increment field because the lock locks out concurrent updates to a singular piece of data. So everybody who's rushing to update a piece of data sits behind the lock gate, and only one execution, one transaction is executed at a time. Now that happens at some rate, some maximum rate, how quickly the database can do that in the operating system environment. The other problem, of course, with relational databases are joins, in a normalized data structure. But the counter has been a hurdle. How do you do distributed counters? Incrementing information on multiple machines, often concurrently, etc., and then returning a single result. How do you do that? So, we've implemented a counter in the CRDT environment, and it works pretty nicely. For example, you can have Europe writing to New York, Asia writing to San Francisco, and let's say you want to count page views. So you have a bucket called page views. It's set up as a counter bucket. The key might be the page, like homepage.html. So every time someone hits homepage.html, you drop an increment +1 to Riak for that piece of data. And that exists in both clusters. So because both clusters, let's assume, are fully active replicated. Now let's imagine someone in Texas, digs a hole too deep and cuts your fiber connection between your clusters, which happens all the time. Europe will continue to write to New York. Asia will continue to write to San Francisco. But now the two values will start to diverge. So you might have started with 100 in both locations, but now there's +50 in New York and +100 in San Francisco. So New York is reading 150, San Francisco is reading 200. What happens ultimately when these two systems come back together? When these two systems come back together, this is the concern in distributed environments. In a last write win scenario, which is a common merge strategy for distributed systems, whoever is the most recent last write will triumph over the others. And this is a known problem and a consideration for folks in this business because you'll lose data. But in our case, we use internal versioning semantics. There's a system called vector clocks. The particular implementation here is DVV, dotted version vector. There's a lot of literature on this, and I apologize for not delving too deeply here. I'm more than happy to continue the conversation afterwards. But needless to say, what happens in the Riak environment is the 150 on one side and the 200 on the other don't become 350. It actually recognizes that it shared the same 100 before they split. So it's 100 plus 50 plus 100, 250. And that's what would happen in a Riak environment. And the main difference between Riak CRDTs or Riak data types and the traditional Riak KV is that Riak CRDTs have this predetermined merge strategy. In the case of a similar scenario with divergence in two clusters or divergence in a single cluster with a KV, with a regular key value, Riak will present both updates to the reader. So when a client will read that piece of data, like user John Smith, which was updated in both data centers, and they diverge, the reader will see both of those writes, and then it's up to you to implement a merge strategy. Okay. Integration with Solr. So I mentioned earlier, if you think of Basho as a distributed computing company, we write our own code, and we also look for best of breed. Solr is best of breed in search. So we had the opportunity to write our own search engine, or simply integrate with best of breed, and we decided to integrate with Solr. And this is something that came along about a year ago now, fall of 2014. And you get to take advantage of everything that Solr gives you. Now the interesting thing here is that Solr and its friend Elasticsearch are not persistent databases. They don't work to keep your data secure on disk in all cases. Riak is. So oftentimes when people implement these kinds of solutions to get the index, get the searching out of Solr or Elasticsearch, they'll do double writes. They'll write to MySQL, they'll write to Solr, they'll write to Postgres, they'll write to Elasticsearch. Inevitably what happens in a distributed environment is those two clusters, your persistent data store, MySQL, Postgres, whatever, and your index, Solr or Elasticsearch, for example, will start to diverge as both of those clusters mutate over time due to failures, etc. The Riak approach, the Basho approach, is to tie Riak and Solr very closely together, very tight integration, such that every installation of Riak, every node in the Riak cluster, has an installation of Solr with it. And the way that Riak recovers from failure, which we discussed, the read repair, active anti-entropy we didn't get to, but it's there. Those repair operations also repair the index. So you have a very tight synchronous coupling between the data on disk and the data in the index. Going back to the concept of search and the product catalog, for example, this is how you might do this. And when I go to speak to customers, it's not a question of replacing relational databases in their environments. It's a question of augmenting their capabilities. You might be in an enterprise that has a tremendous legacy investment in relational databases. That might not be possible to change, nor should it. The question becomes, as product comes to you, business development comes to you and says, hey, there's opportunity to do more new and interesting things. We've collected data in this fashion. It works for this purpose. But now, here's an opportunity to repurpose this data for some other advantage. However, the way that we want to do things might kill our relational database, or it might simply not work. So here's an opportunity for you to introduce new capabilities and features with non-relational systems, with searching, with Redis, with Spark, with Riak. And this is actually a real-world case. The company has a product catalog, does all these things. You have an ETL boundary, you push it out. You materialize those rows as JSON objects via some middleware application that you write. You push it into Riak KV. Riak KV keeps it, and also indexes it with Solr. You expose the Solr search to your web mobile fleet, all these people who are clamoring for your product because these are good problems to have. And then you cache, you amateurize the cost of the Solr search. Anytime you do search, relational, non-relational, Solr, Elasticsearch, whatever it is, it costs, there's a cost associated. What you're trying to do is to, in a caching environment, is amateurize the cost of executing that search over some period of time. So a common design pattern is to cache those search results. So the output of a Solr query is a JSON object. So you just take that JSON object and put it back into the system. So this is some pseudocode that might show you a waterfall of how that might happen. The Solr query itself is like a URL. So everything to the right of the query string, everything to the right of the question mark, is, you can consider it the fingerprint of that query. So you take that fingerprint, you put it through some hashing scenario like MD5 or whatever, get an output, put it in the cache, so in a query cache bucket in Riak, for example, and then execute. Let's take a look at that cache first. If it's in the cache, return it. If it's not in the cache, execute the search, return it to the client, and push it into the cache. That is just a general concept. So it's a general concept as a design pattern, but as we'll see going forward, how we're implementing Redis, and how you can take advantage of that. Okay. Different ways to search for data in Riak. Search, Solr we talked about, secondary indexes we didn't really talk much about, but they're there. There are ways for you to tag items, like for example, if you tag somebody, let's say you create users with a globally unique UUID, but you want to access them by their email. But that's not the key. So you would create an index on the email and then search by email. And there's the search by that secondary index, in this case happening to be email. Another opportunity is MapReduce, which is native internally, but you need to write it in Erlang. But Riak is written in Erlang. But whatever this guy says, there's more stuff. How do we make this better? How do we pull in more technologies to make our application more valuable to you and more valuable to your customers. Faster, stronger, better, all those fun things. This is where the platform comes in. And this is some of the new stuff that we just released like a week or two ago. General availability, it's on our GitHub, you can take a look at all this fun stuff. What the data platform is a number of different things. Relies on some special stuff in Riak KV. There's some new daemons that we put into the system. But let's talk about them specifically and what it looks like. This is actually, one of the best representations I saw of this, and I had a lot of help internally at Basho putting this deck together. I want to shout out to Matt Brender and Kyler Jones internally in Basho who helped me on this deck. And this is a great representation. So if you think of Riak KV, the bottom circle over there, as its own cluster, the Basho data platform actually has other components to it. Right-hand side is Redis, left-hand side is Spark. The top over there, that's the cache proxy to Redis. And lots of different moving parts, but ultimately, the beige node at the top, the service manager, runs on every node in your overall cluster. Some of the nodes in your cluster are part of the Riak KV cluster. Some of the nodes in your cluster are part of the Spark cluster. Some of the nodes are Redis instances. One or more of the nodes are the cache proxy itself. This is, for example, how a little bit of a flow diagram of how that works. The service manager at the top is controlling all the goodies. You can boot up an instance of cache proxy, boot up an instance of Redis, boot up an instance of Spark, the master of the worker. And how it works is, the service manager sits at the bottom, and they're all in unique nodes. So one of them dies, service manager notices that. Service manager is kind of like supervisor deep or forever in Node.js or God. Those supervisor programs that notice when services have died, they bring them back. How to do this with caching? I'm sure many of you are familiar with Redis. It's phenomenal. I love Redis a lot. And it does a lot of really great things. But something that it doesn't do well is scale on its own. Redis is optimized for memory access. It's single-threaded, and it's serialized execution. So that's how you get speed, because everything's memory resident. And that's how you get really interesting data types in Redis. For example, lists, sorted sets, H-stores, and a number of different things. For this implementation and integration point, this is being integrated as a read-through cache. So you're going to write your information to Riak, and you're going to read your information from Redis through the cache proxy. Cache proxy will then accept that read request, check the Redis farm first for that data. If it gets a 200 OK, it's going to pass it on. If it gets a 404 not found, it's going to go to Riak and backfill from Riak. And our benchmarking has basically shown that if you have an 80% hit rate in your cache, you can get like 5 times read speed overall by caching your frequently accessed data directly into Redis. This is kind of how it looks. You have the service manager running all over here. One of your nodes is the cache proxy. The other nodes are actually Redis instances. You have your Redis client sitting out over there, and it's going to make a request to the proxy. It's going to go ahead and do a read from the Redis instances. And how it knows which Redis instance to go to is via pre-caching, and the circular hash there, consistent hash or circular hash used in that environment is actually FNV1A. FNV1A is a consistent hashing algorithm that's not cryptographic strength like the SHA-1, but it's super fast. It's much faster than SHA-1. FNV1A.
For you, Redis, the data to use for Riak or would be getting someplace else?
I'm sorry, can you say that again?
So if you just want to use Redis in the cache layer, do you essentially have to use Riak or can you use it as a separate?
don't think you can write directly into React through the proxy. The proxy looks to fill from React. So you can't write directly to the proxy. That sounds like it's the case. We can follow up with that. But the method here is that Redis, your Redis farm is not a persistent data store. And in fact, the configuration that we use to boot up Redis has no disk persistence. It's not talking to disk at all. Now you can change that, of course. And you can bring your own Redis installation farm to the party with its own configurations, right? With the BG save, background save, or the append-only file. And that's totally on you. You can do that. And then in the cache proxy, you can manually alter that configuration and put in those IP addresses. But part of this whole approach is not just capabilities and functionality. It's also operational management and operational simplicity. All of the products and features that you see here are driven by customers. The reason we decided to design these things is because we heard from customers that this is a pain point for them. The customer will tell us, I'm managing 100 Redis instances, and this is a headache. You know, we work with a lot of customers who have hundreds of instances of all kinds of things deployed. And when you get up to those kinds of numbers, it becomes very complicated. Just from a management perspective, forget about development, functionality, features, all those things. And so there's some inflection point at a certain size where operational constraints dominate all conversations. So considering that, in that kind of environment, we looked to make that less painful. So the Basho Data Platform will install Redis on your behalf. So you don't have to install Redis. You don't have to configure Redis. You don't have to manage the IP addresses. We know how that works. The cache will connect and control and stick in the IP addresses where they need to be, all that fun stuff. Yes, sir?
So, can you still choose which nodes, Redis, or I don't know what software is installed on Solr? So you can specify the best machine type for the job that you use, like AWS?
Yes, you absolutely can. I mean, the nodes that are part of your total Basho Data Platform cluster are of your design.
Yeah, but I mean, like, if I want my React running on like my 2 and I want my Redis.
Yeah. The nodes that need to be homogeneous or the same as far as compute power, memory, storage are concerned are the Riak KV nodes. The other nodes are Redis. So in the Riak KV nodes, you have certain persisted I/O when you're in a virtual environment in AWS. So anytime you run database in a virtualized environment, the overriding concern is I/O. How much of it do you get? So for that reason, persisted I/O in AWS environment is what you're looking for. And on top of that, like the I2 instances have the SSDs. So you have even better, right? Much better. But those might not be the appropriate instance types for a Redis environment or a Spark environment. Spark environment might need more compute. Redis environment might be most likely need more memory. So these are the different considerations, and you can mix and match within a larger environment. Service managers are always talking to other service managers. That's managed through a process called Riak Ensemble. Riak Ensemble is an internal system that copies the configurations of all of the nodes in the cluster to each other node. So every node in the cluster has the copies not only of its own configuration, but the copies of the configurations of every other node in the cluster. So service manager is kind of like the substrate, and everything else sits on top of. The cache proxy and the Redis instance on the Redis side, and the Spark master and Spark worker on the Spark side. Also Riak KV. This is just a flow diagram of what that looks like from the Redis cache perspective. Client to cache proxy, get, if it's there, return. If it's not there, go to Riak and get it and put it in the cache. This one's a little bit more complicated. details. The shipping Redis version is 2.8.21. This is not using Redis cluster. There's no Redis cluster here, which is part of the 3.0 branch. The predominant setting here is the global TTL. Because this is the cache, stuff goes in the cache, but then stuff comes out of the cache. It's not a persistent data store. Persistent data stored piece is Riak. So that's a critical consideration there, depending on your use case. You set that accordingly. I think the default is 15 seconds. Yes. Okay. What else about it? Written in C. This is something that is available in the Enterprise Edition at this point in time. Right now, it's available as a read-through cache. Future implementations, and what we decided, the decision that we made as a company is to release all of it. So we said we want this set of functionality, we want to present it to the community, we want to get feedback from the community. So we're starting with the read-through cache because that's the easiest. Then let's ratchet up the complexity, let's go to a write-through cache, that's what's next. So instead of writing to Riak directly, you write to the Redis side directly, and then it handles the distribution back to Riak. And then we are going to look into taking advantage of specific Redis data types. Right now, we're just doing the straight up key value get put, no data type shenanigans. Now let's quickly hop over to Spark on the analytics side. Spark has become the 800-pound gorilla, and it's eating MapReduce launch all day long. It's kind of like MapReduce 2.0. And I feel like it's gotten a lot of play and a lot of traction because it is data storage agnostic. It'll consume files from S3, it'll consume flat files, it'll consume Hadoop, it'll consume Riak. Look at that. Yes, and the way that it works is via a Spark connector, which we actually just open sourced today. It's a fork of the Riak Java client, and eventually it'll merge back with the Riak Java client when some of this dust settles. But it's open source, you can take a look at it, knock yourself out. And similar to Redis, you can bring your own Spark cluster to the party. Just bring your own Spark cluster, you already got a pre-existing Spark cluster with Zookeeper and the whole thing for. Spark doesn't need Zookeeper regularly. Spark does need Zookeeper in multi-master high availability clusters. It relies on Zookeeper for leader election. And what we've done in the enterprise version of this is, if you notice that little leader election piece in the service manager, we've enabled it such that you can run Spark in a multi-master high availability cluster without Zookeeper. And again, this is driven by customer conversations. Customers came to us and said, we simply don't want to run Zookeeper cluster just to keep the Spark high availability up and running. We just don't want it. Or it's a pain point. We'd rather not do it. So hearing that, we went ahead and implemented the pieces of Zookeeper that Spark environment relies on inside of Riak, such that you can now run this Spark environment without Zookeeper. And it's implemented in Spark as a custom recovery mode. It's currently shipping Spark 141. So it's similar, again, you can bring your own Spark to the party, or we will install Spark on your behalf and manage that whole process. Spark 141 at this point, 1.5 is on the drawing board. The big feature in 1.5 is data frames, and so that's coming. But today it's the traditional Spark minus the data frames. You can get it today as part of the open source Basho data platform packages. Supported our CentOS 7, Ubuntu 14, and I think Ubuntu 12 in production, and Debian and OS X for development. So the bottom line is complexity of application stacks are maturing. The necessity to use multiple types of technologies to provide the kind of features and capabilities to your customers, yourselves, etc., it continues to expand. And if anything, I'd like you to kind of keep in mind that Basho's continuously evaluating the space. And we're either going to build product directly that addresses concerns, or integrate with best-of-breed open source products ourselves. And that's what we've demonstrated here. And it continues to evolve. Some of these things on the left are stuff we already had. The clustering pieces on caching and analytics are the new things that are coming with BDP that are here already. Some of our roadmap and the concept from the company itself is to continuously extend our capabilities through integrations or building actual stuff. So there is some new stuff that's coming. It hasn't been publicly announced yet, but it'll be really, really cool. When you guys see it, a lot of people have been waiting for it. Other opportunities are to integrate with columnar stores, columnar backend storage systems, and graph systems, for example. And these are all on the drawing board. And actually, Best Buy is a customer. So it's not hypothetical, it's actually a customer who's worked through this Solr caching waterfall scenario, and we're currently in conversations with them to expand that to include Redis capabilities, to include Spark analytics capabilities, and revisiting this kind of diagram that we're walking through in the beginning. This is kind of a way that you can simplify your stack. You simplify your backend footprint such that operational simplicity becomes part of your just general mode of doing business. You have your independent Spark, you have your independent Riak KV, you have your independent Redis. They're all tied together through the Basho data platform, and the service manager that's running on all of them has all kinds of admin functionality, and you can see what's happening, and it's all pretty easy. It's actually the ease of use, the operational simplicity is why one of the top reasons why I originally started using React at Columbia, because everybody has finite budgets. And I'm sure we'd all rather be developing applications, extracting efficiencies, etc., rather than babysitting infrastructure. And that's always been my overriding kind of principle when allocating resources, time, money, and people. And finding a system that actually helped me do that, save all of those resources such that I can allocate them in a better kind of way, is the primary reason I picked React. When I was working in the developer seat and I was wearing the developer hat, doing all that stuff.
Are you running open source for the enterprise?
Yeah, personally, we were running open source because we didn't have need for a multi-data center replication at the time for the projects that I was working on. And these are all the things that you get, by offloading reads to Redis, you get more I/O total globally. So ultimately what you're trying to do with any caching solution is extend the total I/O capabilities. So by pushing I/O off disk, pushing it into RAM, you're getting better performance. And Spark is just wonderful. I mean, so much traction, and immediately we were looking for analytics opportunities, and Spark was at the top of the list every time we reviewed this. And the integration work for Spark's been happening for quite some time. It's been about 6 to 9 months in the making, and we're really happy to see it out there and see what people do with it.
You guys are working a lot with database.
So what's interesting about it is it's so well architected and has such very well-defined integration points that we were able to make this happen without a deep connection with Databricks. Yeah. That's not to say it might change, might not change in the future, but as far as I know, I don't think we have a very deep kind of technical relationship there. It's obviously Spark open source and very well documented and specifically designed to interact with multiple data sources. So that's, we're one of now many data sources that will work in the Spark environment. These are some of the logos, we're using React. Because React has traditionally been what I like to call generally applicable. It's not designed for any particular industry, for any particular use case. It's in general unstructured. React doesn't care about what you put into your data. So it's KV where the V is opaque, React is opaque to what you're putting into value. It's multimodal, because KV, but when your value is a document, it's document-based, because you can index those documents in Solr and take advantage of that. So for these reasons, we have a lot of customers in a lot of different industries. And it's been very interesting working with them and hearing their stories and kind of helping them figure out how best to use this kind of technology in their environments. You know, you can go today, this deck will be available, we'll make it available through the meetup. And those links are clicky and you can get to GitHub and you know, download stuff. So, thank you very much.
Let's take some questions.
Questions? All right. Yes, sir.
So what would you say would be a good use case for Riak versus Cassandra and kind of vice versa?
Riak is unstructured by nature. Cassandra has, you know, common structure internally. That's the immediate differentiator. Another key differentiator is the way that these two systems do multi-data center replication. Cassandra has graphical identity, and Cassandra's approach is to spread their ring across multiple data centers. Riak's approach is a cluster of clusters approach. So you have a tight ring in an individual data center connected to another ring in another data center. So there are different approaches there. Cassandra's written in Java. Riak was written in Erlang.
Operation.
Sorry?
Operation.
Sorry?
Operation.
Operational simplicity. What we found in everybody, from my opinion as a developer, opportunities are fantastic. The more opportunities, the more systems that you have in the marketplace, I think grows the pie for everybody. But what we found personally, and what I've personally found is Riak, I hate to say this, and emphasize the operational simplicity. We have a number of customers come to us and reach a certain size with Cassandra clusters, and it becomes more complicated to recover from edge case failures. Certain failure edge cases result in no availability for reads and writes. These are some concerns as far as the expertise you need to run these things, and also Cassandra being written in Java, tuning the JVM is a very so that's oftentimes things that we hear from customers who are coming over to us and saying, how can you help us out here? Does that help answer your question?
Carrying on the operational side, yeah.
Thank you. Well, let's go over here. Yes, sir. Back over there. Thank you.
Why do you favor Spark over Storm?
So
Spark is still transactional, you know, it's still batch entry itself. So why not just go single entry by entry as Storm does?
So oftentimes, customers are implementing these modern architectures called lambda-based architectures, where you are looking to do analysis in multiple different fashions. You're looking to do your real-time analysis, where you're going to bring in a storm to do your real-time analysis as you're ingesting data. It's part of your forward pipeline before the data gets persisted into systems. Spark comes into play when you're looking to do that batch analysis over data at rest. So Storm is operating over data in flight, and Spark is operating over data at rest. Depending on your use cases, you can deploy one or the other or both. And oftentimes customers are doing exactly that, deploying both. I go to a lot of customers who say, I've got Storm, I'm doing this. But maybe there are certain operations that simply cannot be executed on data in flight because it has to then go out and get other data. So maybe they do certain analysis in flight, they do other analysis at rest.
How does it deal with sparse data sets? For example, the hashing algorithm that's, can only be so efficient, it's not equally distributed across all the nodes.
specifically why we use SHA-1. SHA-1 is the math magic behind SHA-1, and this is actually the case, is actually uniform distribution, which is completely different from normal distribution. So yes, when you start, if you look, you can actually boot up Riak, have a watch, do-s, du/s, and look all the stuff in the data directory, and watch as you write key by key, you're testing it, you'll see the files get populated. Actually on the disk, the data directory. Like if you have the entire, you can run Riak, a cluster of Riak of one instance on your laptop. And so it's responsible for the entire ring. So you can see as that data flows into the system, which files are getting hit. As you simply add entropy to your key space, simply, session ID /1, 2, 3, 4, 5, etc. That's that entropy, even at 1 bit, with 1 character. You can see the distribution, and internally in the system, you see that uniform distribution. So it is truly uniform.
Are there any charts that show we have 100 cluster node, here's distribution of data, yet we know it's not guaranteed.
So you'll
it's
actually
uniformly, but not perfectly.
Right. It's not perfect, but the more data you put into it, the more perfect it becomes. It's kind of like rolling dice. Rolling dice, you have the normal distribution around 7, and the more dice you roll, the closer that normal distribution actually hews to the true mathematical normal. The best way I can tell you, just right off the top of my head, is if you have like a 10-node cluster, some n-node cluster, you can actually check the storage. Are the storage considering an equal allocation of the virtual node segments to the underlying physical machines with like an even allocation? You should see that the data consumed on each of those nodes are equal. That's one of the, just right off the top, you can just shell down and see. So that's one of the ways you can just see that that's happening properly.
Okay, so Sasha will be here for one-on-one questions, but that's all the time we have for Q&A tonight. But feel free to come up, talk to him right now. Thank you all for coming.